Good morning. Today's lecture is number 4C. It means that lecture number 4, we took the main lecture, then we took sub-lectures, which is lecture A, B, and now lecture C. Lecture C is called the strap beam. Let's just remember what are the previous lectures. Lecture 4B, combined footings. Lecture 4A, strip footing. Lecture 4, which is the main lecture, it was isolated footings. All of these 4 lectures are part of something called shallow foundations. So we have shallow foundations. Shallow foundations consist of many types. The main type is called isolated footings. What is an isolated footing? If we just look at this, isolated footing is one footing including one column. This is the normal type of footing, and this is the best type and the most efficient type. Because why? Because we use only lower steel. We don't have any upper steel. So in this case, it is very cost effective compared to other types. But sometimes I have problems, like a case of strip footing. What is the case of strip footing? I have one footing like this, but next to it another one, and next to it another one, and so on. Maybe I would have 4 or 5 columns, or maybe I would have a wall instead of the column. So in this case, I need a strip footing. What is a strip footing? A strip footing is similar to the isolated footing, but it will be like this. It will be a very long wall with a footing. It is the same cross-section of the isolated. But if you look at the plan, you will find you don't have here a column. You may have lots of columns next to each other, or just a long wall in this, like a fence. If you have a fence, maybe you would have something like this, a concrete fence. Then it needs a long wall. This is the strip footing. The other type is called combined footing. What is a combined footing? It is just 2 neighboring columns. If I have this column and I have another one next to it, what should I do? If I design each one alone and come to put them on the plan, I will discover that they are overlapping. So because they are overlapping, I need to put them both in one footing, similar to this case. This is a column, this is a column. This is the footing for this one and the footing for this one. They overlapped, so I combined them into one column. Now we are going to go to something called strap beam. Strap beam is another case. It is similar to the combined because they are 2 columns, more or less close to each other. But I have something additional. One of these columns is a neighboring column. What does it mean, a neighboring column? It means that the column is on the edge of my property. Next to it, my neighbor. So in this case, you know that when I have, this is my footing, my column is in the middle, and my column in the middle, it protrudes, the footing protrudes to the right and to the left. Suppose that this is the edge of my land, my property. I cannot construct this portion. In this case, my column will not be in the center of the footing, but it will be on the edge of the footing. So this is a possible case. Somebody would tell me, okay, why not shift the column inside to be in the middle of the column? I will tell you. Imagine that this is the wall at the end of this class, that this wall is the end of your property, and you want to shift the column inside. It means what? It means that you will have the wall of the building, and then after it, with a meter or 2 meters, you will have columns inside. It means you will have columns inside your room. You cannot accept this from an architectural point of view. Your columns should be within the wall. Maybe a little bit protruding from the wall, like the case here. This is the column. It took the thickness of the wall and extended a little bit outside. This is acceptable. But to have the column alone, maybe 2 meters inside the room, it is not acceptable, because you need clear space in each room. So, because we cannot do this, then we need to have a special type of footing called strap beam. Now we are going to discuss what is a strap beam. This is the shape, but we are going to discuss it now in details. This is the first column. This is an intermediate column inside. The column is in the middle of its footing. But here, this is the column that I was speaking about. This is the wall of the neighbor. So my column, of course, I cannot shift it inside. Why I cannot shift it inside? For architectural reasons. So I have to keep it here in this place. In this case, the column is not in the middle of the wall. And you know from a previous lecture for isolated footings that the CG of the column should coincide with the CG of the footing. Otherwise, I will have moment, and if I have moment, it means that this column needs to, or is about to overturn. We'll discuss this now with something. First, this is the shape of the shape of the reinforcement just before casting the concrete. So this is the column at the edge of my site, and this is the footing. This column should have been here at this location, but now I have to put it at the edge. In this case, it is exerting a moment on this footing. And this was the shape of the isolated footings. But when I come to a column, suppose that this is the end of here, this is the end of my property line at this location. In this case, all of this portion will be deleted from my footing, and the remaining will be this part only, and the column is not in the CG of my footing. Just an example. Imagine that one person standing on this wooden raft in the sea, and another one standing on another wooden raft in the sea. Both are supposed to stand where? At the middle, at the CG of the raft. Otherwise, he would fall. The other was supposed to stand here, at this location. This is the middle of this raft. He decided to go one step behind, or maybe more. What will happen? Once he started going back, this raft started to tilt. If you look at let's use a different color here, you will find that the raft is about to overturn. It is about to be lifted from this location and sink from the other location. What is he going to do? What is the first thing he would think of? He's going to sink in the water. He stretches his hand for the person next to him to pull him back. If he managed to do this, if they connect hands, it is called a strap. Strap is a belt. Your watch has a strap. A strap, something to fasten things together. So if I manage to join these two people together, in this case, what will happen? This person is not going to fall. This is exactly what is happening. This is my strap beam. This is the first person who is standing in the middle of his raft, and this is the second person who stands at the edge of the raft. He's about to fall in this direction, so he stretched this strap to connect this column to this column. So this column will end up having a force pulling him in this direction. This force and this force, these two moments cancel each other. So in this case, the column will be standing. So the strap beam is another case of combined footing. Instead of combining the footings together, we are combining them with a strap beam. This strap beam is something like the cements or the ground beams in the soil, but it should be a little bit bigger with higher reinforcement, because it is not just a ground beam. It is a beam that is connecting two columns and preventing one of these columns from falling on the neighbor. So it is exerting a lot of effort. So the cross section here has to be a little big. Just to know the shapes of this strap, here the strap is just a beam on top of the footings. In reality, it may be portion above the footing and portion below the footing, or within the depth of the footing, or it may be fully within the depth of the footing if the footing is big enough. But what is important is the cross section of this beam should be big enough to carry all the force that is required from it. Now, as we've done before in all examples, the introduction is just what we need to discuss, but later what we need is just to go to an example with numbers. So I have two columns. One P1, it is 1,500 kilonewton. The other is 1,200 kilonewton. This one is close to the neighbor. It is not touching the neighbor, but I have a gap. I still have a gap, 1 meter. But this 1 meter is not enough to put a footing. If I try to design this as a normal isolated footing, I will find that my footing would be maybe something like this. I need all of this space, but actually my neighbor cuts part of my footing, so I need to put in this case, if this is my footing, where is the CG of the footing? Here is the CG of the footing. If I cut from it this portion, then this will be the remaining. It means that the CG would be here, and this is the CG of the column. It means that the column is exerting a moment in this direction. So I need to put a strap to connect this column to this column so that it would pull back the effect of this moment. What are the givens? The givens are, this is the load of the first column, the load of the second column, but this load is working load. If you remember from previous designs, we said that we need the ultimate load and the working load. Why do we need both? Because here in Egypt, it is a special case at this time, because we have two specifications, one for foundations and soil mechanics, and one for reinforced concrete. The one for soil mechanics is dealing with working loads. The one with foundations is dealing of RC is dealing with ultimate load. So I need to have both. If I'm just designing the dimensions, length and breadth of the footing, then I am going to deal with the bearing capacity of the soil. So I'm dealing with the the specification or the code for soil. In this case, I will need the working load. But if I'm going to design the depth of the footing or the amount of reinforcement, I'm dealing with RC, then I have to go to the RC specifications or code. In this case, I need the ultimate. So I just multiply by 1.5 to get the ultimate. Later, when our codes are unified and I have the soil mechanics code dealing with ultimate loads, in this case, I will use only the ultimate. I don't have to use both. So please concentrate now at this stage in both loads where to use the ultimate and where to use the working loads, because it is the disaster if you use here the same working load for the design of steel. You will get 2/3 of the amount. It's unsafe. The opposite, if you use the ultimate to get the area, it means that you are increasing 50% of the load. So you have to concentrate. Bearing capacity of the soil, and this is the FCU and F yield of FCU of concrete and F yield of steel. First, I have to check for isolated footings. How to check for isolated footing? I need the area of my footing. I divide the load by the bearing capacity of the soil, get the area. Prove that you need to have this proof. Design this column, get the length and breadth, and prove that this neighbor prevents you from using the isolated footing. In this case, we have to go to the other type of footing. Why do I have to do this? For cost reasons. Because if the cheapest method is the isolated footing. If I leave the isolated and go to strip, strap, combine, in this case, I have to justify the use of this type. So here is the justification. I designed the footing and I found that the distance between the neighbor and the column is not adequate for me. In this case, I cannot use isolated footing. Then I go to the other, the strap beam. How to design the strap beam? To design the strap beam, this is my first load. The blue arrows are for the loads coming from the structure. These are the existing loads. I need to change these blue arrows with these red arrows. What are these red arrows? These are imaginary loads to substitute for the other two loads. But what is the target? My target is to shift this column from this location to an imaginary location so that I would have adequate distance to put my footing. So instead of having two columns close to my neighbor, I'm going to shift one of them inside so that it would be away, a little bit away from the neighbor, and I can put my column. But this is imaginary. It's not in the real case, because if it is in the real case, it will be architecturally refused. So it should be something that I imagine. So this is my imaginarily two loads. The first one coincide with the first red arrow coincide with the first blue arrow. They are the same. But if you look at the value here it was 1,500. After calculation, it is less, 1,366. So in this case, it happened to be less, but it is at the same place. And here, I shifted it. How much did I shift it? I don't know. This is the target of my design. I need to know the exact location where I can put this red arrow so that these two are exactly having the same effects of these two blue arrows. How to do this? Take the moment at this point. If I take the moment at this point, what is the arm of force of these two forces? 0, because they pass. If I tell you take the moment around a point and I have force coming through this point, then in this case the effect of the moment here is 0. Then I end up having only these two forces. One of them I know it, and I know the distance, because I know the original distance between the first force and the second force. But the other one, I don't know the value and I don't know the distance. Then in this case, if I can get the value, then I can get the distance, or at least now I have one equation. This equation includes two unknowns. The first unknown is the value of r, and the second unknown is the distance. If you can give me another equation, it would help me. What is the other equation? Just normal summation of forces. 1,200 plus 1,500, they should be equal to R1 plus R2. To reduce the amount of calculations, this is E, this is the eccentricity. What is this eccentricity? It's a value. By practice, they tell me that take it 0.1 to 0.2 S. S is the spacing between columns. If I have the spacing between columns, say 6.5 meters, then if I take it 65 centimeters, then most probably it will be okay. So I managed to reduce the amount of equation. Instead of going into solving many equations, I'm just going to assume this eccentricity. So I assume a shift of about 0.1 to 0.2, the spacing between columns. So now I know the exact location. So what are my unknowns? My unknowns are only R1 and R2. I don't have any unknowns for distance. I assumed one of the distance. So now, if I take moment around this point, then this value multiplied by this distance, I know. This value I don't know, but I know the distance now. So now I can calculate R1. If I can calculate R1, and I know that the sum of R1 and R2 should be equal to the sum of the original forces, then 1,200 plus 1,500 equals to R1, I calculated R1 by equation now, plus R2, then I can get the value of R2, so now I have R1 and R2. So I managed now to replace these two blue arrows with these two red arrows. So now these are my imaginary footings. What should I do? I should design footings to carry R1 and R2 and not these previous forces. I will need them later, but for the time being, I'm just going to imagine that my two columns are now shifted, one of them in the same place, and the other is shifted by a value of E, 0.65, and I know the new value for R1 and I know the new value for R2. I'm going to use them in my design. I'm going to design a footing here, and I'm going to design a footing here. Once I design these footings, then the remaining, it's normal isolated footings. I don't have any problem in this design. But once I design them, then there is another task. You remember that we said that we have here a strap beam. I need this to design. You design now this footing and this footing. You imagined that you have this column was shifted to this location at the middle, and this column stayed in place. But I'm just going to put it in the opposite direction just to show you that it is the imaginary one, not the. I'm just going to put here. This is my first, and this is my second. This is R1 and R2. So I now need to design this. This is here. The point is the CG of this footing. So I need to design this footing based on R1, and I need to design this footing based on R2. So this is what I'm going to do. I'm going to F1. F1 is the first footing. F2 is the second footing. Normal isolated footings. I'm going to skip it very quickly. The force divided by the bearing capacity, I get the area. This area is length by breadth. I calculate the length, assume any length, any breadth, assume it as assume it as any values you need to satisfy this example. So, but of course, when I come to design this one, I assume that I have an eccentricity of 0.65, and I know the distance from here to the edge of my neighbor, and this is supposed to be the CG of the footing. So now I know half of the footing. 1 meter plus 0.65. It means that from the neighbor to the imaginary column, I have 1.65. This is the midpoint of the footing. If I multiply it by 2, I get the full width of the footing or the full length of the footing, depending on the dimension. So it is 1 plus 0.65 multiplied by 2. So this is the length of my footing. I know one dimension and I know the area. I can get the other dimension. So I now know the length and breadth of this footing, and the other one is straightforward. Take it as a square footing, take it, design it similar to what we usually do. I take the difference between the length and breadth of the footing equal to the length and breadth of the column. Yani whatever you design, it will be accepted. Either use it square or include the length and breadth of the column. Of course here, because we have a strap beam, the effect of the column is not very clear, because when I have a strap beam like this strap beam will the effect of the column, the length and breadth of the column are just inserted inside this beam. So what is reaching the footing is the beam and not the column. The column has no effect directly on the footing. Here, this is the column. The column really does not reach the footing because my strap beam is reaching till the column. So actually, the length and the breadth of the column here are not very important. What is important is that I take the load coming from here, maybe design it as a square footing, it will be accepted. And here we said that I know that this is the location of the imaginary CG. I calculate this distance, multiply it by 2, and then I get the other dimension. So now I designed the two footings. I now need to go to design the strap beam itself. What are the forces? Just for the designing of the footings, I was using the working loads because I'm just designing areas and so on. Now I'm going to design this strap beam. It's a beam. So I'm going to design the depth of the beam. I'm going to design the amount of steel. It means that I need the ultimate load in this case. So, but what are the forces acting on this beam? The forces are, now we come to think of the original forces and the new forces, because the role of this beam, strap beam, is to transfer. This is the beam that is going to transfer these two loads into these two loads. How it's going to do this? By being very strong to take the upper loads from above and transfer them to the bottom to be, the blue arrows act on the beam. and the beam carries the blue arrows and project only the red arrows. How to do this? I need to design this beam. So I need to design a beam carrying this load from top and this load from bottom and this concentrated load from the bottom. But usually when I have a foundation standing on the soil, is it concentrated load or distributed load? It is a distributed load. Why? Because it is not a column standing on the soil, it's a footing standing on the soil. So I need to transfer this load from being a concentrated load, divide it by this area to get the distributed load. So I'm just going to replace R1 with a distributed load equivalent to it, and I'm going to transfer R2 into a distributed load equal to it. What I'm going to have, I'm just going to go to this drawing. If you look at this drawing, these are the blue arrows, this is the strap beam, this is the red arrows equivalent to the blue arrows. I transferred the red arrows from being concentrated load into distributed load coming from the soil. These red but small arrows are distributed load, and this is the same for the other one. So now I need to design a beam. This is the beam. It starts from this point and ends at this point. This is my beam. What is this beam subjected to? From above, it is subjected to this concentrated load from here and the concentrated load from here, and from the bottom I have this distributed load. I need to draw the shearing force diagram and the bending moment diagram. Why do I draw the shearing force diagram? Actually, for one main reason, I need the bending moment. For the design of a footing, you don't need the shear. You mainly need the bending moment. What is the values of the bending moment? I have three values for the bending moment. This is a beam. This here is the beam. It is supported on this column and supported on this column. So this small portion is a cantilever, and this small portion is a cantilever. I can easily calculate this value, and I can easily calculate this value. These are the bending moments on the cantilevers. But now I need to calculate the bending moment inside. I don't know where is the location of the maximum moment. As a rule of thumb, we know from structures that, or from structural design that, or structural analysis, that the maximum bending moment coincides with or is at the location of the zero shear. I get the point of zero shear. This is the point of zero shear. So when I drew this shearing force diagram, I find that the shearing force diagram is zero value at this point. It means that if I calculate the bending moment here, it will be the maximum bending moment. How to draw the shearing force? Beam subjected to column from above and soil from below. First, the load of soil, it acts a little bit alone here, so the load of soil is pushing up. So I'm going to go like this. Once I reach the edge of the column, the load of the column takes the shearing force diagram below till the other edge of the column. Once I reach the other edge of the column, my soil starts to push again till I reach at this location. Once my footing ends, then in this case I don't have any loading. So from this location to this location, I don't have additional loads. So the shearing force diagram will continue as it is, then it will reach the soil again, the soil starts to push, then it will reach the other column starts to push, and then I reach the soil and the soil reach. How to check that I'm correct? That by calculation, this point would be zero, because this is a stable structure. the value of the shearing force coming from above is equal to the value of the shearing force coming from below. If they are not equal, it means that my footing is either going up or going down. So this is my shearing force. This is the point of zero shear. As I said before, I will calculate the bending moment here, the bending moment there, and then I will calculate the bending moment at the point of zero shear. How to calculate bending moment? Force by arm of force. If I want to calculate the bending moment here at this location, so the force multiplied by the arm and the force multiplied by the arm, I get the bending moment. So now I have three bending moments. Now I need to go to the stage where I design steel and design the depth. But similar to what we said before going to this area, check that this footing, according to your dimension, is safe in shear and safe in punching. If it is safe in shear and safe in punching, then you can design the steel so that you don't have to redesign the steel again. So similar to what we said before, to check the shear, it means that I go to my footing, check the locations where I have, if I have this footing, where is the location where I have, I need to check the shear. I can check the shear at this line. This is the maximum shear. I can check the shear at this line. This is, just a moment. I can check the shear at this line. This is another line I can check. Of course, according to my dimensions, I will know which is more critical. Usually this is the critical distance. So I calculate the shear according at this line. Here I don't have shearing in this direction, but I may have shear in this direction. So I will check which is the critical and check the shear. What about check of punching? You remember what we said about check of punching? What is this is something not related to this lecture. It was related to the isolated footing. Do you remember the example I gave you? How to differentiate between shear and punching? I'll just give you a reminder. If I give you a bar of chocolate and I tell you, give me a piece of it, you will shear this bar to give me part of it. So shearing is taking a part of a big body, exerting a force on it so that it would be sheared into two pieces. I would take the smaller piece. But what is punching? Punching is not, in sense it is a shear, but the way it is applied is different. It means that if I have a bar of chocolate, a big bar of chocolate, and I just put my thumb on it, I want to penetrate it. In this case, you will find that you need to exert a lot of effort. If I give you a bar and I tell you, give me a piece, you will just maybe give me a small piece. It will be easy for you to shear it into two pieces. But if I tell you, press hard so that you would penetrate it, it needs a higher force. Usually check of shear is more critical than check of punching, but it's not a rule. In some cases, the shear is okay, but the punching is unsafe. But this is just to differentiate between both cases. So now I have, as I said, I have the three moments. I need to design many things. We said that we are going to check shear. We are going to check shear for both footings. And then if the shear is okay, we are not going to check punching, we are just going to design directly. Why don't I have check punching? Because how come the column will penetrate the footing if I am having a beam at the bottom? This beam will prevent the column from punching the footing. So usually I check only the shear and not the punching in this case. So this is the calculation. For the calculation of the reinforcement, how many reinforcements I need to calculate? I have, if I call this F1, and this is F2. F1 and F2 are just normal isolated footings. So I need to calculate the bottom reinforcement of F1 and the bottom reinforcement of F2, just to show you what will be the shape of this reinforcement. It will be something like this. This is the bottom reinforcement in this direction, and this is the bottom reinforcement in the perpendicular direction. So these are, of course, many bars next to each other. This one is repeated all along this depth, and this bar is repeated all along this depth. So this is my reinforcement. Which one, to design this, I need to calculate the bending moment from this cantilever. To design this, I need to calculate the bending moment on this cantilever. Once I calculate F1 from both directions, maybe one of them is minimum steel. You have very small amount of moment, and because if you have a moment here and a moment there, you will design based on the bigger moment. So this is for F2, the same for F1. I have reinforcement from here and going like this to the other side. So this is the reinforcement for F1, and I have maybe minimum reinforcement in the other direction. Why did I say minimum reinforcement? Because this strap beam is preventing I don't have any cantilevers. Here I don't have a cantilever, and there I don't have a cantilever. In this case, I don't have moment in this direction. I only have moment in this transverse direction. So this is the first thing I need to calculate. So this concerns F1 and F2. But now I have also the strap beam. This is the additional point that I need to design here. F1 and F2 are normal isolated footing. The only difference is that I shifted this column to be an imaginary column with an eccentricity here. And I designed F1 based on this new load, and F2 based on the new load. Now I need to design the strap beam. As I said before, the strap beam was subjected to 3 moments. This is the first moment, this is the second moment, this is the bottom reinforcement. If I want to put reinforcement here, imagine that I have here a strap beam from this point to this point. The bottom reinforcement, it will be here. Here is my bottom reinforcement, something like this. This is my bottom reinforcement. Which moment will affect this bottom reinforcement? I can call this M1. I can call this M2. So I will take the maximum of M1 and M2 and design the bottom reinforcement. What I need to design the upper reinforcement. The upper reinforcement is here. It is something like this. This upper reinforcement, I am going to use this moment here. Call it M3, whatever it is used in this example. I will use this moment to calculate the upper reinforcement. So this is exactly what we are going to do. We are going here. We designed F1 and F2, the reinforcement of F1 and F2. But before that, we calculated the reinforcement for the strap beam. You check the shear, and this is the top reinforcement and the bottom reinforcement. Let's just check the moment. What is the value of this moment? 873. This is for the top. Let's go and check here. If you look at this value, it is 873. So I use the top moment to calculate the top reinforcement. For the upper, I have here two moments. I took the bigger one, this bigger one, and I used it to calculate the bottom reinforcement. Of course, any location where I don't have maximum moment, then I design based having a minimum reinforcement. Then I design F1 and F2 as I told you. Then I would end up having this. This is my first footing. This is my second footing. This is my original force. This is my imaginary force. I design this footing based on this imaginary force, and I design this footing also based on the imaginary force that is smaller than this one. It is at the same location, but it has a different value, and I have a strap beam. This strap beam will have a bottom reinforcement, and it will have an upper reinforcement. I need to put the upper and bottom reinforcement in this strap beam. These reinforcement are what resembles this case. This upper and lower reinforcement will act as the strap that would connect these two people to stand straight, or these two footings to stand straight. This is the shape of the reinforcement in case it taken from the Egyptian code. Here it is given in Arabic, here it is given in English. This is how we put the reinforcement in the footing and the reinforcement in the beam itself, because this is a normal beam that have upper and lower reinforcement. It will be something like this. This is the beam, this is the upper reinforcement. Here the upper reinforcement are much than the lower reinforcement, because the bigger moment, if you remember, where is my bigger moment? I will go to this drawing for the moment. Yes, here you will find that usually the middle moment is very high compared to the two cantilevers. So in this case, the big amount of reinforcement will be the top reinforcement of the beam, and here a lower amount for the bottom reinforcement. This is blow up for the beam. This is the beam. This is all of this is the upper reinforcement. This is the bottom reinforcement of the beam, and with this drawing, we now know everything about the strap beam, how to design it in details. As you can see, it is only a beam that we designed based on a bending moment, including three bending moment diagram, including three moments, one in the middle and two cantilevers. I take the maximum of the two cantilevers to design the bottom. I take the middle to design the upper reinforcement. So this is for the beam. For the two foundations, this is my new location of my imaginary load, and this is the same location of my imaginary load. The load here is different from the original, and the load here is also different from the original. I will design two footings based on these values, on these new values, and I will put only lower reinforcement. Anyone, if you are required to draw something like this and you put an upper reinforcement, it means that you don't understand that this is just a normal isolated footing. So it is very easy. It is just an application for an isolated footing. You need to know it because you are going to face it when you come to work in the industry. So you need to have a reference so that you can refer to it in case you need to design a strap beam combined footing, strip footing, plus your original isolated footing. Thank you, and see you next lecture.